Now we're going to look at two specific tools that can be used to perform calorimetry. The first one is constant pressure calorimetry. Now that constant pressure is just the pressure, the atmospheric pressure. This is what's called a coffee cup calorimeter. This is what we would use in our lab. If you notice, there are two styrofoam cups. You've got a thermometer there. You've got water that's filling the cup. And the system itself is going to be the reactants that can be dropped into the water, resulting in a reaction. So your system is the reactants and the products that they form. The surroundings are going to be water and the calorimeter itself. Now we're going to assume for coffee cup calorimeters or constant pressure calorimeters that the styrofoam cups are good insulators, are perfect insulators, so we're going to assume that there is no loss of heat when this reaction occurs. What happens in a coffee cup calorimeter is that the water, when the reaction occurs, the water can either increase in temperature or it can decrease in temperature. If the water increases in temperature, that means that the system, the reactant, released energy when the reaction occurred, and therefore the reaction is exothermic. If the water temperature decreased, what that means is that the reactant absorbs energy from the surroundings, from the water, and therefore the reaction is endothermic. So this equation right here is crucial in completing these calorimetry problems, specifically if the solution absorbs energy, if it absorbs heat, then that is going to be equal to the heat that the reaction lost, negative of it. If the solution releases energy, then that's going to be equal to the heat that the reaction absorbs. So the Q of the solution equals simply the negative of the Q of the reaction. So let's look at an example in which we actually use this. So this is a coffee cup calorimeter question. And what it tells you is that you're dissolving 6.5 grams of sodium hydroxide into 100 grams of water, and that water is in a coffee cup calorimeter. So I'm going to draw this very briefly, just to make sure we're on the same page. So you've got your calorimeter, a crude drawing of a calorimeter. You've got your water, and it's 100 grams of water. And then into that 100 grams of water, you're going to dissolve sodium hydroxide. So I'm going to show little dots of sodium hydroxide. And the mass of that is 6.50 grams. Okay. And what this problem tells you is that the temperature of the solution rises from 21.6 degrees Celsius to 37.8 degrees Celsius. And we know that it's the temperature of the solution because that's what the thermometer is going to be in. So, based on the equation that we looked at before, we know that the heat that the solution absorbs, that's going to equal the negative of the heat of the reaction. So what I'm actually going to do in this problem is I'm going to solve for the heat that's absorbed by the solution, and then the negative of that will just be the heat that is released by the reaction. So we're going to start off, I know that my formula is Q equals mc delta T. Okay. The mass of my solution, it's not, you might be tempted to say it's 100 grams, but it's not, because I don't have 100 grams of solution, I have 100 grams of water. The total mass of the solution is the 100 grams plus the mass of the sodium hydroxide. So the mass of my solution is going to be 106.5 grams. Okay? In this problem, it tells you to assume that the specific heat of the solution is just the same as that of pure water. Pure water has a specific heat of 4.184 joules per gram degree Celsius because it's specific heat. Now I'm going to multiply that by the change in temperature. Now my final temperature, my TF, is 37.8, and my initial temperature, my TI, is 21.6. So when I subtract 21.6 from 37.8, I get my delta T to be 16.2 degrees Celsius. Notice that makes sense since I am increasing the temperature. So my delta T that I'm going to put here is 16.2 degrees Celsius. Now when I multiply all of those together, what I get is 7,218.7 joules. Now before I move on, if you notice my final answer, it's asking for kilojoules per mole. So I'm going to quickly convert these joules into kilojoules. I know that for every 1 kilojoule, there are 1,000 joules, 10 to the third joules, which means that this is going to be 7.2187 kilojoules. And since I want only 3 significant figures, because 16.2 has 3 sig figs, it's going to be 7.22 kilojoules. Now, this is the heat that the solution absorbs, which means that the heat that the reaction released is the negative of that, so negative 7.22 kilojoules. Now, I'm almost done, except for the fact that this problem asks me for the change in enthalpy in kilojoules per mole, and right now I'm just in kilojoules. So if you notice, this amount of heat is released when 6.50 grams of sodium hydroxide are dissolved. So I'm going to say 7.22 kilojoules per 6.50 grams of NaOH. Now, right now, my units are going to be kilojoules per gram, but I don't want that. I want kilojoules per mole. So all I have to do is one more step of dimensional analysis. I'm going to get rid of grams by putting them up top, and I'm going to put 1 mole on bottom. Now this relationship is the molar mass of NaOH, which is 40.00 grams. And so when I multiply, I get for my change in enthalpy negative 44.4 kilojoules per mole, and that's my final answer. So keep in mind the couple of quirky things about this problem. First of all, when I'm calculating the heat of the solution, I need to consider the mass of the entire solution, not just the solvent or the solute. And when I'm finding the change in enthalpy in the end, instead of just having it in kilojoules, if it asks for kilojoules per mole, you acknowledge the fact that 7.22 kilojoules of energy are being released per 6.50 grams of NaOH that are dissolved, and therefore using that assumption you can then calculate how many kilojoules per mole are going to be released.
The second type of calorimeter is a bomb calorimeter, and in a bomb calorimeter the volume is kept constant. So if you look at this mechanism right here, what you have is one container inside another one. That container, which didn't exist in coffee cup calorimetry, is called the bomb. It's the reaction chamber where the reaction occurs. So what happens is that you put a sample into the bomb, into the reaction chamber, and you fill the chamber with oxygen. Then you put electrodes into the reaction chamber and allow it to ignite the sample, resulting in a combustion reaction. Now, combustion reactions release energy, so as a result, the water is going to increase in temperature. So bomb calorimetry enables you to determine the amount of heat that is released by that combustion reaction by measuring the change in temperature of the water and therefore relating that to the heat that is released by the combustion reaction. There is one important difference between bomb calorimetry and coffee cup calorimetry, other than the fact that the actual tools are different. Number one, bomb calorimetry is a lot more exact. In addition, instead of assuming that the heat capacity of the solution is the same as the heat capacity of water, which we do in coffee cup calorimetry, we have to be given the heat capacity of the calorimeter. So let's look at another example, this time of bomb calorimetry.
Here is an example problem of a bomb calorimeter. In this problem, it tells you that you have 1 gram of N2H4, and what it tells you is that the calorimeter is going to increase in temperature by 3.51 degrees Celsius. And it also tells you that the heat capacity of the calorimeter is 5.510 kilojoules per degree Celsius. Notice this is not specific heat because it's not per gram. It's not molar heat capacity because it's not per mole. What you need to remember is the fact that the heat that the calorimeter is going to absorb, that equals the negative heat of the reaction. And so what we're first going to calculate, since we're given the increase in temperature that the calorimeter experiences and the heat capacity of the calorimeter, we're first going to calculate the heat of the calorimeter. And all we have to do here to calculate that, the heat of the calorimeter, is take the heat capacity, which is 5.510 kilojoules per degree Celsius, and we're going to multiply that by the change in temperature, which is 3.51 degrees Celsius. And so what we find is that the heat that the calorimeter absorbs is 19.3 kilojoules. Now, if I want to find the heat of the reaction, that is just going to be the negative of that. So the heat of the reaction is negative 19.3 kilojoules. Now, it's kind of complicated because here it says calculate how much heat was released. Well, 19.3 kilojoules were released, but if we're talking about the change in heat, it's negative 19.3 kilojoules. Next, it asks you to find the heat of combustion of 1 mole of N2H4. So this is similar to the problem that we previously did with the coffee cup calorimeter. I know that 19.3 kilojoules is going to be released for every 1 gram of N2H4 that reacts. Therefore, to calculate how many kilojoules per mole, I need to put moles on bottom, and I'm going to put the molar mass up top, which is 32.052 grams. And that allows me to determine the heat of combustion, which is kilojoules per mole. And what I get once I multiply is negative 619 kilojoules per mole of N2H4.